Hello, and welcome to Differential Equations. This is Lecture 21, Row Operations. Last time, we talked about matrices and determinants. This time, we're going to talk about matrices and systems of linear equations. Suppose we want to solve the system of equations given by 3h plus 2m plus L equals 39, 2h plus 3m plus L equals 34, and h plus 2m plus 3L equals 26. Right? We can rewrite this, given what we saw last time, as the product of a matrix times the vector of unknowns, HML, equals 39, 34, 26. Right? So this system of linear equations can be written as a single equation of a matrix times a vector equals a vector. Right? So this is called the coefficient matrix. And another matrix associated to this system is what's called the augmented matrix of this system. So to get this matrix, all we're going to do is add a column where we're going to include the right-hand side of the system. Okay, so now the strategy for solving this system of equations is to perform simplifying operations on the system, but always in such a way that we don't change the solutions, right? So these operations are called row operations. So these are going to be three operations that do not change the solutions of the equations. Okay, so I'll mention what we're doing at the level of equations, which will make it clear solutions don't change, and then what that means at the level of the augmented matrix. Okay, so first, you can add a multiple of one equation to another. Right? If you do that, that's not going to change the set of solutions to your equation. And as far as the augmented matrix goes, that's the same as adding a multiple of one row to another. Right? The second thing that you might do is multiply both sides of an equation by a non-zero constant, right? Or equivalently, at the level of augmented matrix, multiply a row by a non-zero constant. And then finally, you can switch the order that two equations are written in, and that certainly won't change the set of solutions, which at the level of the augmented matrix means that you can switch the order of two rows. Okay, so now the idea is to use these operations to get the augmented matrix into a form like this one, right? So if you can get the augmented matrix to look like this, so that here you have every row just has a single non-zero entry before the augment, and those are on diagonal, and then here you have just some constants, then we didn't change the set of solutions because we only used these row operations. But if we translate this back to equations, then the first equation just says H is equal to C1. The second equation says M is equal to C2. And the last one says L is equal to C3. And so we've solved the system of equations, right? Of course, you might not be able to get the augmented matrix into this form. So if not, you try to get as close as possible. Okay, so let's carry this out in this example. So in this case, we start out with first column is 3, 2, 1, then 2, 3, 1, and 2, 3, 2, sorry, and then 1, 1, 3. And then we augment with 39, 34, 26. So what we'll do first, switch row 1 with row 3. Right, so row 3 ends up here. Row 1 ends up down here, and row 2 is unchanged. Then we're going to subtract multiples, or maybe I'll say add multiples of row 1 to rows 2 and 3. Right? So what I'm going to do is I'm going to use this 1 to clean up this column. So I want this column to end up just having 1, 0, 0. Right? So, okay, nothing is going to change for the first row. Here, I'm going to multiply. So to get rid of that 2, what I'll do is multiply the first row by -2 and add it to the second row. Right? So it's going to give me a 0. Then 2 times -2 is -4. Add to 3, I get -1. 3 times -2 is -6. Add to 1, I end up with -5. 3 times 26, sorry, -2 times 26, add to 34, that comes to -18. And then I'm going to do very similar. I want to get rid of this 3, so I'll multiply the first row by -3 and add it to this one. And that'll give me 0, -4, -8, -39. right? Now, the second row starts with -1. I prefer for it to start with a 1, so I'll multiply row 2 by -1, right? So nothing happens to the first row. The second row becomes 0, 1, 5, 18, and nothing happens to the third row. Right? So now I will add multiples of row 2 to rows 1 and 3. Right? So I have this 1 that I like. I want to clean up its column. So I want to make this a 0 and this a 0. So for the first row, what I'm going to do is multiply this row by -2 and then add it to the first row. Right? So I'm going to end up with 1, 0, then -7, then -10. Nothing happens to the second row. And then to get rid of this -4, what I'm going to do is multiply this row by 4 and then add it to this one. So I'll end up with 0, then 12, and then 33. Okay, so wonderful. So next we look at this 12. We'd rather that was a 1. So we'll multiply row 3 by 1 over 12. Right? So nothing happens to the first row. Nothing happens to the second row. And the third row becomes 0, 0, 1. And then 33 divided by 12 is the same as 11 divided by 4. Okay, and now I will add multiples of row 3 to rows 1 and 2. Right? Because I have this 1 that I like, but I want the rest of the column to be zeros. So I'm going to multiply, to get rid of this -7, I'm going to multiply this row by 7 and add it to this one. So here I'm going to end up with 1, 0, 0, and then 37 divided by 4. And then here I'll do, for the second row, I'm going to multiply this row by -5 and add it to this one. So I'm going to end up with 0, 1, 0, and then 17 divided by 4. And then nothing happens to the third row, 0, 0, 1, 11 divided by 4. So now this translates, if I translate this back to equations, this translates back to the equations h equals 37 divided by 4, m equals 17 divided by 4, and L equals 11 divided by 4. Okay, so this algorithm where you work one row at a time, right? So with the first row, you get the first non-zero entry to be a 1, and then you clean up its column. And then you move to the second row, you get its first non-zero entry to be a 1, and then you clean up its column. And then you go to the third row, you get its first non-zero entry to be a 1, and then you clean up its column. That algorithm is called the Gaussian elimination algorithm. Okay, so let's name what these matrix forms are called. So let's say that a matrix is in row echelon form, right? Abbreviated REF, if first thing I want is that every row containing a non-zero entry is above every row which contains only zeros. Right, so if you have a row of all zeros, I want that row to be at the bottom of the matrix. And then secondly, right, so echelon means something like steps or like stairs. So that's what we're going for. We like this sort of staircase pattern. And so I want if I is less than j, then the first non-zero entry in the ith row is strictly to the left of the first non-zero entry in the jth row. Right, so this is in row echelon form because the first non-zero entry of each row occurs to the left of all of the non-zero entries in rows above it. Okay, we call the first non-zero entry in a row a pivot. Right, so over here, the pivots were all on at the first column. Right over here, this is a pivot, this is a pivot, this is a pivot. Right, once you're here, then this is a pivot, this is a pivot, this is a pivot. So already here, our matrix is in row echelon form. Of course, we kept going. So a matrix in row echelon form is in reduced row echelon form, abbreviated RREF, if, so now I'm going to ask that every pivot is equal to 1, right? So this matrix fails because this pivot is equal to 12. And then I want any column that contains a pivot contains no other non-zero entry. Right? So that's why we kept going all the way to here, because here, every column that has a pivot has no other non-zero entry. Okay, so now using the Gaussian elimination algorithm, every matrix can be put into reduced row echelon form. So let's do another example. Suppose you wanted to solve the following system: x plus 1/4 y plus 1/2 w is equal to 20. 2x plus 1/4 y is equal to 36. and x plus 8z plus w is equal to 176, right? So if we write this as a matrix vector product, then our coefficient matrix would be 1, 2, 1, 1/4, 1/4, 0, 0, 0, 8, 1/2, 0, 1, right? So this column corresponds to the x's, this one to the y's, this one to the z's, this one to the w's, right? So then it's multiplying x, y, z, w, right? Notice that this is a 3 by 4 matrix, so you need a column of size 4 to multiply, and when you do, you have 3 by 4 times 4 by 1, so the product is going to be a 3 by 1. So here you end up with 3 entries, and indeed the right-hand side is 20, 36, 176. Okay, so let's say we want to solve this system of equations. This has augmented matrix. Right? So basically just this same coefficient matrix. But now I augment it with the right-hand side of the system of equations. Right? And now if you do row operations, you can bring this system into the following RREF. Okay, and this translates back to equations as x equals 16 plus 1/2 w, y is equal to 16 minus 4w, and z is equal to 20 minus 3 over 16 w. Right. So notice what I've done here when I translated it back to equations is I'm keeping on the left-hand side the variables that ended up with pivots in their column, and then the variable w, right, which got the 4th column, it doesn't have a pivot in its column, right, because this matrix has pivots right here. So no pivot in this column, so I put that one on the right-hand side. Okay, so here w is what's called a free variable, right? That's what we call a variable that ends up without a pivot in its column. And we have solved for x, y, and z in terms of w. Here, x, y, and z are pivot variables. Right? So a pivot variable is one such so that in the reduced row echelon form that you ended up with, you have a pivot in its column. Okay, so the reason we do that is that then if you want to write down what the set of solutions is for this system of equations, all right? So you could say the solutions are all of the vectors x, y, z, and w, where x is given by 16 plus 1/2 w, y is 16 minus 4w, z is 20 minus 3 over 16 w, and w is just w. And then you can write this as the terms that do not have a w plus w times the coefficients of the terms that do have a w. Right? And here w is free, so w is allowed to be any real number. And this gives us all of the solutions, right? You pick any real number for W, and you can plug that into here, and you'll get a solution to this matrix vector equation, or equivalently to this system of linear equations, right? So that's why we keep the free variable, right? And that's why we call it free. It's free to be whatever real number you like, but for every real number that you choose for W, you get explicit values for X, Y, and Z. Okay, so this is what it looks like when a system of equations has more than one solution, and indeed this has infinitely many solutions. Let's look at what happens when you try to do Gaussian elimination and your system doesn't have any solutions, right? So let's do an example where it's obvious that there are no solutions. Let's say that you wanted to solve 3x plus 4y equals 6 and 3x plus 4y equals 7, right? Well, those can't both be true, but let's see what happens if you try to do Gaussian elimination, right? So we can translate this to a matrix vector equation. We have the matrix 3, 4, 3, 4, multiplies the vector xy, results in the vector 6, 7. Okay, so this has augmented matrix. Three, 4, augment 6, 3, 4, augment 7. And you can do a couple of row operations to get this to reduced row echelon form. You end up with this. Right, and now if you translate this back to equations, right, we have two equations. The first one, the first row translates to x plus 4 over 3 y equals 2. And the second equation translates to 0 equals 1. Right, well, 0 equals 1 is an obvious contradiction, right? So that contradiction shows you that your original system didn't have any solutions. So in terms of pivots, notice that our pivots in this reduced row echelon form are here and here, right? So when you look at the augmented matrix, you don't want to ever have a pivot in the final column, right? Because if the final column has a pivot, that means that its row has only zeros in the variable columns. And so that means that when you translate back to equations, you're going to have 0 equals 1. That's a contradiction. Can't happen. So that's what it looks like when you don't have any solutions. Let's look at the same system, but what if I wanted to have infinitely many solutions? Like, let's say you just repeated an equation. So we had 3x plus 4y equals 6, and then I gave you as a second equation 3x plus 4y equals 6, and you didn't notice that I was just repeating, right? Or you wanted to just see what would happen with Gaussian elimination, right? So here, as a matrix vector system, it looks like 3, 4, 3, 4 times xy equals 6, 6. Right, this has augmented matrix. 3, 4, augment 6, 3, 4, augment 6. And its reduced to echelon form looks like 1, 4 divided by 3, augment 2, and then 0, 0, 0. Right? This translates to x plus 4/3 y equals 2, and 0 equals 0. 0 equals 0 is perfectly fine. It doesn't give us any information, but it also doesn't give us a contradiction, right? So here the x is a pivot variable and the y is a free variable. So we can write the solutions as all of the vectors x and y, where, so we're going to write the pivot variable in terms of the free variable, right? So x is equal to 2 minus 4/3 y. Y is just equal to y, right? And I can write this as 2, 0 plus y times minus 4/3 1. And here y is free, so it's allowed to be any real number. And that's the set of solutions to this equation. So we've seen what happens when you have a single solution, right? That's when you have a pivot in every column except for the last one. Right? We've seen what happens here when you have multiple solutions. So that's when you have a free variable. What happens when you have no solutions? So that's when you have a pivot in the final column. Right? And then this one was another example where you have infinitely many solutions, right? We ended up with a free variable. So if you have, as long as you don't have a pivot in the final column, you're going to have infinitely many solutions if and only if there's a free variable. Right? Notice that in these last two equations, we see that for the matrix three, 4, 3, 4, the matrix vector equation A times the vector X equals a vector B sometimes has no solutions, and sometimes has many solutions. Infinitely many, as it happens. If, on the other hand, a matrix A is invertible, well, here, let me call this matrix M, just to emphasize that I'm not talking about this matrix A, but just an arbitrary matrix. Then the equation mx equals b always has exactly one solution. Namely, if you have mx equals b and m is invertible, well, you can just multiply both sides by the inverse and find that x is equal to m inverse times b. Okay. So one way of finding the solution in the case that m is invertible then we can solve mx equals b using Cramer's rule. So this has come up before. This was named after a Genevan mathematician. So his name is properly pronounced in French. So Gabriel Cramer, who lived from 1704 to 1752. Right. And what this rule says is that the ith coordinate of this vector x is equal to the determinant of, let's call it m sub I, divided by the determinant of m, where m sub I is the matrix obtained by replacing the ith column of m with the vector b. So for example, the solution to the equation we solved in a previous example, using Gaussian elimination, is given by, well, H would be the determinant of, and all we need to do is replace this first column by this column. So it would be 39, 34, 26, and everything else stays the same. And we divide that by the determinant of this coefficient matrix, right? M would be a determinant of the matrix we get by replacing the second column with the right-hand side. So first column stays the same, and then we put this column, and then we put the third column, divide by the determinant of the coefficient matrix. And L would be the determinant of, since it's the last variable, you replace the final column with the right-hand side. So 3, 2, 1, 2, 3, 2, and then the right-hand side, 39, 34, 26, divided by the determinant 3, 2, 1, 2, 3, 2, 1, 1, 3. Okay, so Cramer's rule is nice in that it is direct, right? You can find the value of the third variable, say, directly without having to compute anything else. However, Gaussian elimination is far superior in that it requires fewer operations. It works for non-invertible and non-square matrices, right, for which the determinant doesn't make any sense. And it gives a lot more information. So, for example, we've talked about the null space of a matrix in the previous lecture. The dimension of the null space is equal to the number of free variables. In the reducible echelon form of a matrix. The rank of a matrix, which is not something we're going to talk about, but it's a measure of how large the range of the map multiplying by a matrix is the number of pivots in the reducible echelon form. So an advantage of doing Gaussian elimination is that you find the reducible echelon form, which you don't if you're using Cramer's rule to solve systems with determinants. For that matter, Gaussian elimination is also how we compute inverse matrices. Right? So if you have an invertible matrix, right, you could use this method to solve, or you could also multiply by the inverse. So that begs the question, how do you find the inverse? Well, when the inverse exists, you can use Gaussian elimination to find it. And Gaussian elimination will also tell you whether or not it exists. So for example, suppose you wanted to find the inverse of the matrix, call it A, this same matrix, 3, 2, 1, 2, 3, 2, 1, 1, 3. Here's what you do. We put the following matrix. So put the matrix A and then augment it with the identity matrix. Then put this matrix into reduced row echelon form. And what you would get would be the identity matrix followed by 7 over 12 minus 5 over 12, 1 over 12, then minus 1 over 3, 2 over 3, minus 1 over 3, minus 1 over 12, minus 1 over 12, 5 over 12. Right? So here you started out with A augmented with the identity, and then at the end you end up with the identity augmented by A inverse. Right? And again, Gaussian elimination also tells you whether or not the inverse exists, because what you can do for any matrix, whether or not you know it has an inverse, is form this augmented matrix, right? A augmented with the identity, and put it into reduced row echelon form. If you did not end up with the identity on the left, that means that the matrix A is not invertible. If you did end up with the identity on the left, that means that the matrix A is invertible, and whatever is on the right, that's the inverse. Okay. Row operations also provide an efficient way to compute determinants. Right? So remember, we have 3 row operations. So let's think about what they would do to the determinant of the matrix. Adding a multiple of one row to another does not change the determinant. So you can do that row operation all you like, and it won't change the determinant. Changing the order of 2 rows multiplies the determinant by -1. And finally, multiplying a row by a non-zero constant multiplies the determinant by the same constant. So the idea to compute the determinant is to use row operations until the matrix is upper triangular. Right? So what's that mean? That means that every entry below the diagonal is 0. Right? And then use that the determinant of an upper triangular matrix is the product of the elements on the diagonal. It doesn't matter what the size of the matrix is. If it is upper triangular, then the determinant is the product of the elements on the diagonal. So let's work out an example of a 4x4 matrix. Suppose you wanted to find the determinant of the matrix A, 4x4, with entries -1, 5, 2, 0, then 2, 0, 1, 0, then -3, 2, 1, 3, 4, -2, 2, -2. Okay, so to find this determinant, what we could do is, I'm just going to copy it again down here. Okay, so I'm going to do row operations, trying to get this upper triangular, right? And I'm going to do this trying to only use add multiple of one row to another, because that doesn't change the determinant at all. So I'm going to add multiples of row 1 to rows 2 and 3. So nothing is going to happen to the first row, right? The second row, what I'm going to do is multiply this row by 5 and add it to this one, right? So I'd end up with 0, then 10, then -15 plus 2 is -13. Then 20 minus 2 is 18. Then what I'm going to do is, to get rid of this 2, is multiply this row by 2 and add it to this one. Right, so I end up with 0, 5, -6 plus 1 is -5. And then 4 times 2 is 8, plus 2 is 10. And then I'm not going to do anything to the last row. Okay, perfect. So I'm looking for upper triangular, right? So I need to kill everything below the diagonal. So next I want to get rid of this 5. So I will add a multiple of row 2 to row 3. Right? So nothing is going to happen to the first row. Nothing is going to happen to the second row. The third row, I'm going to multiply, I need to get rid of this 5. So I'm going to multiply this row by -1/2 and then add it to this one. So I'll end up with 0, 0, then 3/2, and then 1. And then nothing is going to happen to the last row. And then finally, right? I'm looking for upper triangular, so I just need to make this one a 0. So I'll add a multiple of row 3 to row 4. And so I have nothing happens to the first row, nothing happens to the second row, nothing happens to the third row. And this one, I'm going to multiply this row by -2 and add it to this one. So I end up with 0, 0, 0, and then -4. Okay, so since none of these steps change the determinant, we know that the determinant of A is equal to the determinant of this final matrix, which is equal to the product of the elements on the diagonal, because this matrix is upper triangular, right? And if you multiply those out, you get 60. Okay, so if you count how many operations, now here I had a few operations less because this row had some zeros. But worst case scenario, if you're doing Gaussian elimination, you count how many sums and multiplications you need to do to get your matrix to be upper triangular. In the 4x4 case, I think it works out to around 40 sums and multiplications you have to do in the worst case. If you do Laplace expansion, then worst case scenarios, you have to do around 72 sums and multiplications. So almost double the number of sums and multiplications to compute the determinant of a 4x4 matrix. On the other hand, if you use that this matrix has a couple of zeros on the fourth row, then you only need half as many operations for your Laplace expansion. So that's like 36. So that's just fewer than the worst case number of operations for doing it with row operations. Let's compute the determinant in that way. So using Laplace expansion of the fourth row, we would get, okay, determinant of A, right? So 0 here and 0 here. So the first term is going to be, right? So, okay, this is row 4, right? Down to here. And then this would be element 4(1), element 4(2), element 4(3), and element 4(4). So since I start with 4(3), I do -1 to the 4 plus 3 times this one times the determinant of the matrix you get by removing this row and this column, right? So this would be -1, 5, 2, 2, 0, 1, 4, -2, 2, right? And then I do plus -1 to the 4 plus 4 times the 4, element times the determinant of the matrix you get by removing this row and this column. So it would be -1, 5, 2, 2, 0, 1, and then -3, 2, 1. Right, and so this ends up being -3. The determinant of this matrix you can work out is 10. And then I end up with plus -2 times the determinant of this matrix, which you can work out as -15. Right, so that's -30 plus sorry, this determinant should have been -10. So I end up with 30 plus 30, which gives me 60. Right? So you compute the determinant in these two different ways, but it takes many fewer operations to do it using row operations. Okay, so that's what I want to say about row operations. We're going to use this a lot next time when we talk about eigenvalues and eigenvectors. The most important thing is going to be using row operations to solve systems of equations. We're going to be solving a lot for the null space of a matrix. Okay, but we'll do that next time.